All right, everyone, welcome to my talk. My name is Wulf. I'm from the IT University of Copenhagen. I'm a postdoc there, and today I'm going to present to you my result that computing the polytope diameter is even harder than NP-hard. So let's jump straight into it. What do all these concepts mean? So I will assume that you're familiar with the simplex algorithm, which is a very famous algorithm for linear programming. It maximizes a linear objective over a given polytope, and you can imagine the simplex algorithm as walking from a vertex to vertex. So if you can imagine you're maybe like an ant crawling on the surface of the polytope, and you want to hop from vertex to vertex and want to find the vertex that maximizes the objective in the target direction. And of course, an important choice if you are situated at a vertex, which vertex to visit next, and this choice is not fixed in the simplex algorithm. There's a so-called pivot rule that determines which vertex to visit next. One obvious choice is to visit the vertex which increases the objective function by the most amount, but maybe this choice is not the best choice. Maybe it's too greedy, right? So a lot of different pivot rules have been proposed for the simplex algorithm, and even though so many of them have been proposed, for every single one we know a worst case example that needs an exponential time of steps, or at least a super polynomial amount of steps, right? So a lot of research has been done on different pivot rules, and for all of them we know bad worst case example. And this is related to this super famous question of Smale, who formulated as one of the driving questions for the 20th century. Is it possible to do 21st century? Is it possible to do linear programming in strongly polynomial time? And maybe surprising to some listeners is that the simplex algorithm is still a candidate algorithm for this conjecture. So it could be that there exists a pivot rule that takes a strongly polynomial amount of steps. We just haven't looked in it. We're not smart enough to find the pivot rule. Nobody has ruled out this possibility yet. So it could actually be that the simplex algorithm could resolve Smale's conjecture. You could ask your colleague if they think that is likely or not, but to the current state of knowledge, that is a possibility. And related to this concept of strongly polynomial linear programming is the so-called diameter of a polytope, the main topic of today's talk. So let's say you're given two vertices on the polytope V and W. We imagine we are this bug on the polytope and we want to crawl from V to W. Let's call the distance of V and W the amount of hops I need to take to reach V from W, so the amount of edges I have to traverse. So in this example, the distance is 3. And then the diameter is simply the maximum possible distance that can be attained, so the maximum distance over all vertex pairs of the polytope. And what is immediately obvious is that any lower bound on the simplex algorithm runtime is given by this diameter under any pivot rule, right? So no matter how you choose the next vertex to visit, you will certainly need at least diameter many steps in the runtime of the simplex algorithm, simply because the simplex algorithm has this global structure that at every point in time, it jumps from vertex to vertex. This means if we find a good lower bound of a diameter of a polytope, we know that the simplex algorithm needs to run many steps, no matter which pivot rule it uses. So here's an example. We can consider the d-dimensional hypercube. It has 2 d bounding planes, but 2 to the power of d vertices, its diameter is d. And so the fact that this diameter is d is kind of like every 2 binary strings have a distance at most d. But here you can see a phenomenon. I can describe the hypercube with 2 times d bounding planes, but still the amount of vertices is exponential. And this will be an important property of these high-dimensional polytopes, that you cannot figure out the diameter simply by constructing the graph, because the graph has an exponential amount of vertices, right? So this is why this question is so tricky. And this is related to the so-called Hirsch conjecture, which is a very famous conjecture in this field, proposed in 1957 by Hirsch, who conjectured that all polytopes P, if they live in dimension D and have n facets, then the diameter of the polytope Hirsch conjectured would be at most n minus d. Now, today we know that Hirsch conjecture is false. It was disproven first partially and then fully in 2012. But we know counterexamples only in a very weak sense. So the strongest counterexample we know to this Hirsch conjecture is polytope that violates this diameter bound by a factor 21/20, right? So it's only very slightly larger than Hirsch conjecture. And this made people conjecture maybe a more relaxed version of the Hirsch conjecture, which is, but maybe if we replace this n minus d with any polynomial in n and d, then maybe it holds, right? So the conjecture is that for all polytopes p in d dimension with n facets, the diameter of the polynomial, the diameter of the polytope is at most some polynomial in n and d. And this is one of the most famous open questions in polyhedral geometry. And if you think about it, this is actually a prerequisite for the simplex algorithm to be able to run in strongly polynomial time, right? Because if there exists some polytope whose diameter is not even polynomial, then of course the simplex algorithm on this polytope will not be able to run in strongly polynomial time. But somehow the consensus in this field is people believe this strongly polynomial Hirsch conjecture, and they put a lot of effort into proving it. And there's a lot of partial work done on this polynomial Hirsch conjecture. The best known bound that is known today is an expression of the form n minus d to the order of d divided by log d by Sukegawa improving on earlier results. But this is not the main topic of today's talk. But what is actually the topic of today's talk is also a very intriguing problem, because this Hirsch conjecture is asked about the diameter of a polytope, right? But also a very fundamental problem is the decision problem associated, or the computation problem associated to actually computing the diameter, right? So here I would ask you, I give you some polytope given in this half-space description. So I give you some matrix A, some right-hand side B, describing some polytope P. So for example, this could be the hypercube, which you could describe with only very few hyperplanes. And then my question to you is, for some given threshold parameter T, is the diameter of this polytope at most T? And as I hinted at before, the main difficulty of this question is that I can, with very few hyperplanes, describe very complex polytopes with an exponential number of vertices. So this question seems very tricky. And in fact, already in 1994, Friese and Tang asked, what is the computational complexity of this decision problem, computing the diameter of a polytope? And also, some previous results exist on this question. So Friese and Tang themselves showed in 1994 that this problem is weakly NP-hard. Sanita at FOCS 2018 proved that it's strongly NP-hard already for a simple family of polytopes, the so-called fractional matching polytope, whereas Friese and Tang, they could show this result only for a handcrafted family of polytopes that had no known name. And then very recently, Nöbel and Steiner could improve this result. They could show strong NP hardness already for the even simpler family of the bipartite perfect matching polytope. But none of these authors could actually answer the question whether this decision problem is actually contained in the class NP, right? So usually the NP hardness part is the hard part of a proof. But here, none of these authors could show containment. And in fact, this is no surprise, because already in 1994, Friese and Tang conjectured that this problem is actually above the class NP. So it's complete for a larger class than the class NP. And in fact, this is our main contribution of this paper. We show that the decision problem of computing the diameter is hard for the second level of the polynomial hierarchy, which is a class that I will explain in a minute, and lies above the class NP. And this is true already when we restrict our attention to the bipartite perfect matching polytope. So as a consequence, this decision problem of computing the diameter is sigma 2 complete for the bipartite perfect matching polytope, and it's sigma 2 complete for all polytopes if the polynomial Hirsch conjecture holds. So this is some technicality that for the containment in sigma 2, we need actually the Hirsch conjecture to know, but we know that the Hirsch conjecture is true for the bipartite perfect matching polytope. So for this family of polytopes that I will mainly talk about today, this result is really tight, and I suspect that this result is tight in general, but we would need to know the polynomial Hirsch conjecture to really know the tightness for the general class of all polytopes, but I don't want to go into too much technical details. And this is our main result and answers the long-standing question by Friese and Teng raised in 1994. So we'll talk a little bit about what is actually this larger class. Some people here may be familiar with it, some people may not be familiar with it. So let me quickly repeat how I think about the class NP. Think, for example, about the Hamiltonian cycle problem. It asks, does there exist a Hamiltonian cycle in the graph? And if the answer to my question is yes, then I can give you a witness that verifies that my answer is yes. If the graph actually contains a Hamiltonian cycle, I can give you a set of edges and you can verify whether my proposed witness is a Hamiltonian cycle. And so this means a word is contained in the language if and only there exists a witness that verifies membership. And for example, this could be the property that W describes a Hamiltonian cycle, and this property should be better testable in polynomial time. And now Stockmeier defined the so-called polynomial hierarchy, and today we are only concerned with the second level of the polynomial hierarchy, which is all words which admit the following pattern. Something is contained in sigma 2 if and only if for all, if there exists a witness of the form for all W1, there exists W2, such that some property depending on the instance and the witness W1 and the witness W2 holds. Okay, so here's an example. Diameter decision is a fit to this class of problems because the diameter of the polytope is small if and only if for all vertex pairs VW, there exists a short path from V to W of length at most T. Why do we care about this class of problems? And I'm gonna here follow the argumentation of Wigginger, who said that we need to think more often about this class sigma 2. And the reason is that integer program solvers require superpolynomial size models to solve sigma 2 complete problems. So that means that today we are kind of at the threshold where we need more and more powerful methods. And also we need to think if you encounter such sigma 2 complete problems, integer program solvers might not be the right tools for solving them. And there's been a lot of recent activity in the area which I've been involved with, which also got me interested in this topic to start with. And there's also a lot of other related work. So if you care about the hardness of computing the distance between two vertices instead of the diameter, this is sometimes hardness reductions in this regime can be easier. There's also been a lot of related work for different families of polytopes, approximation or exact computation. And our results also relate to the area of so-called combinatorial reconfiguration of perfect matchings. I hope this becomes clear in a second why that is the case. All right, so let me actually try to give you a small hint of the proof. We're going to talk about the bipartite perfect matching polytope. So here we are given a bipartite graph, G, and then we're going to think about all the perfect matchings of G, and we're going to think about the characteristic vector of the perfect matching, and then the convex hull of all the incident vectors of all the perfect matchings. This defines us some polytope. It's a very well-known polytope, and today we want to talk about what is the diameter of this polytope. So we first need to understand, given two vertices on this polytope, when it is the case that these two vertices are neighbors. And it turns out, this is well known, these two vertices are neighbors if and only if the symmetric difference is a single alternating cycle. In general, the symmetric difference could be multiple alternating cycles. If the symmetric difference of the two perfect matchings is a single alternating cycle, then and only then these two vertices are neighbors on the polytope. This is a well-known fact, proven by Schwartal. So this leads to the following maybe visualization. So let's say we're given some matching M, we select some alternating cycle C with respect to M, and we flip the edges of that cycle, meaning we exchange red and black edges. Then M prime results from M by something that we call a cycle flip. And then the distance between two perfect matchings M1 and M2 is simply the shortest flip sequence starting from M1 and ending at M2. So here's some clarification, because this confused me also at the start. So let's say you have two perfect matchings M1 and M2. You look at the symmetric difference. In general, this could be multiple cycles. In this example, it's 5 cycles. And this tells us that the distance of M1 and M2 is at most 5. But it could be the case that the distance of M1 and M2 is even smaller. So we could find, for example, one very complicated cycle and flip along this complicated cycle, then find another also complicated cycle, flip also along the second complicated cycle, and somehow we achieve the same result, right? And this also shows you that the polynomial Hirsch conjecture holds for the bipartite perfect matching polytope. And the tricky part is figuring out when is the case that the distance of M1 and M2 is even smaller. And this is the thing that is so hard to compute. So to summarize, we want to compute the diameter of the perfect matching polytope, which is the maximum flip distance of any two perfect matchings of the given bipartite graph. And how do we show hardness of such a question? That is, of course, the main question. And here I'm going to refer to an elegant idea of Nöbel and Steiner that they used already in Soda 25. So they introduced these gadgets, which they called tower gadgets. And then these tower gadgets can be in two configurations, the start and the target configuration. I mean, in general, there can be many configurations, but Nöbel and Steiner highlighted these two specific configurations. And something I should also mention is that these two tower gadgets, they are connected to the rest of the graph only in these two vertices. So if anything interacts with the tower gadget, it has to enter here and leave here. Now, if you want to get from the start configuration to the target configuration, you could go with option 1, which is select this single cycle at the top and just flip this single cycle. Then you will end up in the target configuration. You could also alternatively go with option 2. You could start at the bottom, select this alternating path, flip it, and select this alternating path, flip it, select this one, flip it, select this one, flip it, and so on. Select this, 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 this. And at the end, you will see you will end up at the target configuration. No, on the first side, it looks like option 1 seems clearly better. But the point, the clever idea of Nöbel and Steiner that option 1 is locally restricted. So it means it will help only for this one tower. It will not be globally efficient. And they argued that if you have a huge amount of towers, but set the desired flip distance, which you're testing for, to be small, that this means that an average alternating cycle in the flip distance must visit all towers. Basically because the cycle has to be globally efficient. If it would flip only a single tower, it's only locally efficient. But because we have such a huge amount of towers, this will waste resources, right? So let's say we have a huge amount of towers arranged in a line like this. Let's call this a city gadget, because clearly a lot of towers equals a city. And now the main idea is that the city gadget, it forces the alternating cycles that flip from one perfect matching to another matching to visit this city, right? So you have some city, some location that the alternating cycle has to visit. And this will be the first ingredient in our reduction. And the second ingredient of our reduction is that I, together with Christoph Grüner, and based on earlier work of Berit Johannes and Jim Orlin, studied the structure of a typical sigma-2 complete problem. And by our study, we were motivated to look at the variant of the Hamiltonian cycle problem, which is sigma-2 complete. So of course, the Hamiltonian cycle problem is only NP complete. Let's consider the following variant. In this variant, we are given a directed graph H, and we are given special vertices V1 up to Vk that are vertices of H. And let us say that the out degree of every vertex is fixed to be 2. And then let's say that the pattern is, if I select from each of these special vertex one of the two outgoing edges. And let us further say a Hamiltonian cycle respects this pattern if from every special vertex it chooses exactly the edge that has been selected. And then I can ask the following question: is it true that for all patterns there exists a Hamiltonian cycle with exactly this pattern? Okay, certainly a question you can ask, and based on arguments I had on this earlier paper, we showed that this variant of the Hamiltonian cycle problem is complete for the second level of the polynomial hierarchy. So here's the reduction idea in full. We are given a directed graph H. We want to redefine a graph GH such that for all patterns there exists a Hamiltonian cycle with this pattern in H if and only if for all perfect matchings M1 and M2 in the new graph the distance of M1 and M2 is small. Okay, so that's the general idea. The patterns correspond to perfect matchings, and the Hamiltonian cycles correspond to small flip distance. And the main idea is that we introduce so-called for all gadgets with some special property that they can model this behavior. So we will show that for any two perfect matchings M1 and M2, the flip distance of M1 and 2 depends most importantly on the structure of M1 and M2 restricted to the for all gadget. And furthermore, if M1 and M2 are two perfect matchings that maximize the flip distance from each other, then the gadget can only be in one of two possible states. And this is already a slight simplification in the paper that is not true, but for the talk, I will teach it like that. So somehow the way we can imagine is that in the extremal configurations where the two perfect matchings have the maximum distance from each other, the for all gadgets is one of these two configurations. So somehow the second matching will always be the same, and the first matching is either in this or this configuration. And then based on this, we are given this instance H, where we have the variant of the Hamiltonian cycle problem, and then we construct the new graph GH, where we introduce a lot of city gadgets for the locations that have to be visited, and we introduce a lot of for all gadgets with a property that we find like before. And how do these for all gadgets look? They are quite complicated. They look like this. So the cycle enters here and exits in either one of these two edges. And somehow we show in the paper that in extremal configurations, it's very important what the matching looks like with respect to the inner part of this gadget. So the inner part is actually the biggest part of the gadget. It's just for sake of clarity, it's not drawn as the biggest part. And we proceed to show that if you have an alternating cycle that visits every city, so is efficient in the sense that I described earlier, then there's actually only two possibilities for the alternating cycle to interact with this gadget. Either it interacts with it in a top state and it needs to leave the gadget on a top edge, or it interacts with the gadget in a bottom state and it interacts and leaves the gadget in the bottom edge. And then the next ingredient that we need so-called XOR gadgets to enable this behavior that I showed on the previous slide. So if this is kind of like a standard idea from Hamiltonian cycle. If some cycle visits every city, then the XOR gadget, the cycle has to either traverse the bottom edge or the top edge, but can never traverse both edges. You need to introduce these to model the behavior of this for all gadget. And then the second ingredient is that you have a bunch of which we call ladder gadgets. And these are the representing the inside of the for all gadgets. And the point is that the ladder can be bottom open or top open. And it starts in the bottom open or top open states and it wants to go to the default state. But somehow, if it's in the bottom open state, then it's more efficient to go to the default state if the alternating cycle comes from the bottom, right? So a ladder that is bottom open, it's most efficient if it's visited from the bottom. So this is somehow how we introduce this asymmetric behavior that we need from the for all gadget. And there's some applications. There's a variant of the circuit diameter a variant of the polytope diameter called the circuit diameter, which allows for additional directions to move. So I will not explain the technicalities, but somehow in this variant, you're also allowed to move sometimes through the interior of the polytope according to certain rules. And it's a relaxation of the diameter. Because it's a relaxation, it has also gained a lot of recent interest. So there's a lot of papers studying this relaxation. And our result also applies to the circuit diameter, also based on an idea of Nöbel and Steiner, because it turns out that it's simply the case that for this bipartite perfect matching polytope, the circuit diameter is equal to the diameter. So that's kind of nice. Whenever you show a hardness result applying to the diameter, it automatically also applies to the circuit diameter. So this is this theorem. Circuit diameter decision is sigma 2 complete already on the bipartite perfect matching polytope. And then the final part of the paper, which I did not talk so much about in this presentation, we also show an inner proximability result. For diameter, already inner proximability result was known, but it was on a different class of polytopes. And now we also know the inner proximability for TU constraint matrix and inner proximability for the circuit diameter. Note that our two main results are incomparable because inner proximability is a stronger statement, but here we all have only NP hardness instead of sigma 2 hardness. So to come to a conclusion, we showed that the diameter for the bipartite perfect matching polytope is sigma 2 complete to compute, and this answers the long-standing open questions. There's some open questions left, so we don't know the hardness for simple polytopes, which are polytopes where every vertex has only dimension many neighbors. Somehow this bipartite perfect matching polytope is very highly non-simple. There's also some variant, which is called the monotone diameter, which is also left open by this work. A big open question is whether there's a constant factor approximation for the diameter. And you could also ask whether it's possible to combine our result. Can you get an 1 plus epsilon approximation? Can you show that this is sigma 2 hard to compute? Somehow you would need to combine inner proximability techniques with sigma 2 techniques. All right, thank you for your attention.